Hello, everyone. I hope you had a wonderful day here in the United States and everywhere in the world, wherever you are starting a new day. So my name is Mohammed Qasim. I'm from Efabless. Wanted to welcome you today for our webinar with Dr. Hammond Pearce about using LLMs for hardware design and different tips and tricks. And it's in the context of the challenge that the keyword spotting challenge that is currently running for generative AI by Efabless. And so Dr. Pearce is going to go with some examples and things that examples that he has worked out offline, and also you're going to show some of them live. I wanted to thank our co-sponsor and partially the who's sponsoring a silicon with Efabless, premise.ai. They have sponsored the silicon, one of the silicon manufacturing slots, as well as they have provided the pro level access to RapidGPT, their LLM based design chat engine. So we're gonna talk today with listen to Dr. Hammond Pearce. He is from University of New South Wales in Sydney, Australia. He's specializing in cybersecurity and embedded systems and cyber physical security related to the additive manufacturing and all the impact of machine learning related to these types of applications. And he, Dr. Pearce and his team, and a team from NYU, New York University, they have been the winners, the #1 winner of the first challenge that we've launched last year for generative AI. So I'm going to give Dr. Pearce the screen. And please go ahead and if you have any questions, put them in the Q&A section, and then we'll have some time at the end to do.
All right. Thanks very much, Mohammed. So hopefully people can hear me, if that's good. Yep. Yep. Okay. So let me share my screen and let's get right into it. All right, so thanks very much. Today I'm going to be doing a quick webinar on how to approach the particular hardware challenge that you guys are hopefully participating in, and also just general tips and techniques, and maybe a little bit of history about using large language models for hardware as well. So on the right-hand side there, you can actually see the GDS file, which was our chip that we designed and taped out, which was actually 100% authored by ChatGPT. So who am I? A little bit more. So currently, as Mohammed said, I'm a lecturer at the University of New South Wales. Previously, I was a research assistant professor at New York University over in the United States. And then prior to that, I was completing my PhD at the University of Auckland in New Zealand. So why are we all here? I think we can all agree that AI and in particular, large language models are definitely on the cusp of, some kind of transformation, and that how we interact with computers and how we interact with our computing tools, such as our EDA software or almost, normal computer software code and things like that, is changing because the nature of the interaction can now be done through AI and through large language models, in which we can just talk to them and get that kind of stuff and those kinds of interesting new automation. And so my research in particular explores how we can redefine this EDA engineering process based on this new large language model technology. And in particular, I'm interested in answering the question, what do we need before we can have AI that can help us design hardware sort of reliably and robustly? Of course, having machine learning in EDA is not anything particularly new. Machine learning has been used throughout EDA for quite some time, basically since machine learning was available. And we've been using it for all kinds of EDA tasks. So design and netlist optimization, doing test point placement, doing layout optimization, doing performance optimization. All of these things have had AI in them for quite some time now. And so it's no real surprise when we say, well, we've got this new technology now, we've got these large language models, and we're interested in knowing whether or not we can bring those into the hardware design process too. So all of this kind of started back in 2020 when large language models like GitHub Copilot, actually in 2020 it was GPT-2, right? GPT-2 was the first language model that came out where people could say, hey, this is actually starting to be able to produce meaningful code. And so what I'm interested in knowing is how do we start to measure the performance of these large language models, and how do we start to know whether or not they can see interesting outputs for us? And the evolution of AI has continued over this time, right? We've gone from GPT-2 to GPT-3 to OpenAI's Codex, to eventually GitHub Copilot, ChatGPT, Llama, and so on and so forth. I can see a couple of you in the audience have just raised your hands. I think the correct interaction, if you can just put your questions into the Zoom Q&A box, that would be fantastic. So conversational large language models came out with ChatGPT in 2022. And these are the ones where we started being able to instruct the models, right? So we could actually, rather than just kind of exploit the properties of a large language model and that it predicts the next word, to actually kind of start giving them instructions and leverage that for them to complete tasks. So we had these, really interesting outputs that started to come out. People were measuring ChatGPT and Bard and saying that they could pass coding interviews, medical interviews, they could write really interesting prose. And they also, around this time started being able to produce artwork on demand and things like that too. So it's been a really, really interesting and expanding ride. So the question that I want to know is, can we start, thinking about how to use these large language models for hardware design, right? So here what we want to do is put in some prompt, and this is the input to the language model, right? We then talk to this language model, we get some results, some design file, and then we can try and verify that design file, or we can try and synthesize that design file. And if the verification is not, 100% what we're after, we can run this in a loop where we can try and improve the prompt, or we can change the prompt, or we can have a conversation based on the prompt, and we can actually start to do this kind of iterative design process. And eventually we'll be happy with our verification, and we'll head over to synthesis and try and produce our design and see what that comes out. So if you're not 100% familiar with how large language models even work, I'm just going to give a very, very brief, and I promise it's brief, crash course in the whole process, okay? So in general, large language models are trained over very, very large amounts of text, right? And the text can be anything textual. So it can be the internet, it can be books, it can be textbooks, it can be open source code repositories, it can be open source hardware code repositories. And so from all of this text that they are trained over, they build a statistical model of what that text looks like. And as it turns out, we can use that model to start predicting the next word if we've got something that's not quite finished, right? So this is a nice example here. If you have got some input to a language model and you say, can you please come blank, you can ask that language model what's a reasonable word to come next. And that word that comes next could be something like over, or it could be cut here, or it could be out. And to answer that question of what word comes next, these models are just trained over an enormous amount of normal text. And that can expand as you increase the size of the model, the number of parameters. So if you hear about, ChatGPT becoming a trillion parameter model or whatever, and people are getting excited that these models are getting bigger and bigger, it's because these models can start to remember and operate over increasing amounts of data. And so that gets to the point where you can start with these models and actually give them questions like recite the first law of robotics. And because GPT-3 has seen a Wikipedia page or a book, or even even the book itself that it was presented in, it can actually say, well, the reasonable thing to come next here is actually that first law of robotics, as penned by Isaac Asimov. So this is a little bit how that guess the word game works, right? So I can put in some word on a language model that's trained over code, and here by word I really mean a small piece of code like say int. And if this was your only input to a language model, there was nothing else in it, you might say, well, if I was going to write the next word, maybe the next thing I would do is put main, right? So int main. The nice thing is now we can run this in what's called an auto-regressive loop. So we can actually say, hey, int main, let's put that back in. And now the language model thinks that the next thing might be an open parentheses. And so then we can put that in, and now it thinks maybe it would be a closed parentheses, and so on and so forth, right? And so this kind of guess the word game and guess the next thing game, this is really all that's happening under the hood in language models. And from there, we can go to so much more. Okay, that's it. That was my whole crash course, so I hope you enjoyed it. Okay, we've now got a large number of large language models that exist, right? There's a fair number of them in the open source world for normal stuff. So you've seen things like Llama, you've seen things like CodeGen, maybe you've heard of Salesforce's models, maybe you've heard of the NVIDIA models. Most people have at least heard of ChatGPT and say GitHub Copilot, but actually, as it turns out, there's a lot of other models too. And there's now actually an increasing number of models that are trained particularly for hardware. And again, by training, what we mean is that they've in that training corpus where they learned over all of the text, there was just a fair amount of hardware stuff in that text. Okay, so there's some academic open source models like Dave and Verilog, which have come out of research done by my team. There's also other models like RTLLM and MEVLLM that have come out of other research groups. And, I encourage you to look at their work too, because it's super interesting. There's commercial and proprietary models. So Synopsys and Cadence have both produced models. NVIDIA brought out a paper with a model called ChipNemo. And of course, Primus AI, who is nicely sponsoring one of the parts of this competition, have brought out Rapid GPT, which is one that I'm going to be playing around with in this webinar today. And then also, of course, there are models like, as I said, ChatGPT and GitHub Copilot, which, while they're not specifically tuned for hardware, actually, it turns out are quite good at working on it anyway. I think it's clear to see why so many people are interested in producing these large language models and kind of joining in this rising tide of AI. And that's because the AI just seems to be so good at what it's doing and quite fun and easy to use. And so already we've seen in languages like Java and Python, a huge amount of code is being produced using tools like GitHub Copilot. As GitHub Copilot themselves produced a study, they said that about 50% of the developers that have tried this tool keep using it. So there's a certain amount of stickability there where people think it's definitely helping out. Okay, so this is the fourth Efabless AI challenge, and I did say that this talk was mostly going to be about some tips and techniques you can go to try it out. I just wanted to briefly mention some of the ways that other people have approached these problems in the past. So certainly I can talk about how I approached the very first challenge, which was using ChatGPT when it first came out. But actually, you'll see here that an enormous amount of the winning entries over the past 3 challenges have all been made by ChatGPT until the last one, when someone put in the 3rd place entry, which was based on Bing Chat. And so what we're really interested in seeing is that these other models sort of catching up to where OpenAI has been for the last little while, right? So it really has been OpenAI's ChatGPT as kind of the standard bearer for producing both software and hardware in many ways. And so it's interesting now that we're seeing more models rising and appearing over the last year. We've seen Llama models and so on and so forth. So hopefully in this entry and in competition 4, we'll see other large language models too. Okay, so how do we even get started, right? I think this is the most beginning important place to begin with, right? So what we want to do is actually try and produce some hardware straight off the bat. So what I'm going to do is I'm going to Alt-Tab out of my presentation and into a Visual Studio Code window, but not that Visual Studio Code window. I want this one. Okay, so I'm actually just going to delete the code that's in here, to be honest, because I want to actually produce new code, but that's my test bench, so I'll leave that for now. So I've got some thing that I've set up here, right, which is a module that you can see here, and I'll zoom in a little bit to make the font a little bit bigger. Hopefully you can all read that. All we've got is just a blank module right now, right? So I've got some definition of a name here. It's called iStick, and the reason for that is because I'm going to hopefully synthesize this and put it onto an ICE40 FPGA. And I've just got a clock and some LED outputs. Now, I actually had some confusion with trying to use RapidGPT, I'll be honest, because I was expecting it to work a little bit like GitHub Copilot, where you just got suggestions continuously. But as it turns out, RapidGPT works a little bit differently. And you put what you want it to do in a /* comment at the top here. So I'm going to say that I want to make and I'm going to make it a 32-bit timer for now, a 32-bit up counter, which emits the top 5 bits to the LEDs D1 to D5. And I'm going to leave this module definition here. Now, I did try this earlier, but I keep changing how I'm prompting, so who knows what will happen. Okay, so I'm going to delete that. Okay, now hopefully, there we go. So I've got a pop-up that says RapidGPT is doing something. So let's see what it comes up with. Okay, we've got that. Great. So what it looks like it's done is it's produced a design for us. So that's nice. And it, broadly looks like what we wanted. There's a counter, and the top bits are going out to the LEDs. So I do have a test bench. I made this test bench earlier. And if I, all it does is it just puts in a clock. So if I run this test bench, what we should see is hopefully the simulation working, right? So I can just go make simulate view. And what that will do is it will give us a GTK window here. And what I can do is just add my waves, and you can see some output. But actually, you can't see any output. So there's a problem. And we can see that all of these are just undefined at the moment. They are the value X. And so we might go, well, why has that happened? But actually, it's pretty clear why it's happened. If we go back to the design that it's made here, it hasn't initialized this counter to be anything. And, partly that's on me. I never gave it a reset signal. But I'm going to now try get it to fix this design. Okay, so I'm going to head into the RapidGPT thing. I'm just going to delete my old chats. These were the ones I was practicing with. Okay, so my counter doesn't simulate. It just outputs X. Okay, so let's see what RapidGPT comes up with here. We'll hopefully what it should tell us is that we need to put an initial block, or realistically, the easiest thing to do would just be to define that counter equals 0 here. So we'll just have it's added an initial block in there. Okay, so that looks good. So this was another trick that I had to work out, which wasn't immediately clear from the interface. So there's this merge code button here, and we can push that. And then you want your code here. And to actually get your code, you actually click this button that says revert this change, which is a very strange UI decision. But that's how you actually get the code that it's suggesting into your file. So I push revert, which is not the verb I would have used. And now if I head back into my design, we'll see it's added an initial block, which I think should fix this. So I've closed the simulation. So we'll just run that again, make simulate view. And we'll just re-add that. So this is all open source stuff, by the way. Okay, fantastic. We can see the counter is incrementing. And eventually, right, the top LEDs are going to be emitted, but that's going to take a while. But I have confidence that that will now work. Okay, so that's good. Now, what I want to do is test this out by deploying it to my FPGA. I also have in my list of files here, I have a little bash script which will synthesize my project, and it will send it down to an ice stick FPGA. And why I picked this particular FPGA today is it actually uses Yosis and stuff for the synthesis. And Yosis, of course, is the open source synthesis tool that OpenLane uses, which is what Paravel uses. So it's a nice place for us to start from, because we know we're using roughly the same tool that I would be using for Paravel. So what I'm going to do is I'm going to run this bash makeit.sh file. And what that's going to do is it's going to synthesize using Yosis my design, and it's going to push it down onto an FPGA. And what I have got here is a live camera feed of my FPGA, but not very much appears to be happening yet. And so we go, well, that's a bit irritating. My first LED came on. So what have we learned? Well, probably my clock is running a bit too slow to be a 32-bit timer, right? So let's head back and ask our good friend RapidGPT to change this again. So this is running a bit slow for me. Can you make it, let's say, a 24-bit timer up counter instead? All right, so let's try that out, and we'll see whether or not that this one works. But that was a pretty promising start, in that we got our first little LED blinking, which is always a good place to begin. So let's see. It's having just a little bit of a think. Okay, we want to, yes, that is exactly what we want to do. We want to turn it from 32 bits into 24 bits. So now this is a bit painful, because what I'm going to do is I'm going to hit this merge button again, and then I think I have to do all of the changes bit by bit, which is a little bit painful. So I'd really like an approve all button, or in this case, a revert all button, but there isn't one that I have found. Although I think you can go over here, which is a little bit quicker, but it does still say revert, which is a bit strange. Okay, revert. There we go. So I've got my 3 changes in now, which is good. And so let's try synthesize that again. And here we go, it's programming. Oh, look at that now. So hopefully you can see now on the webinar. Okay, the camera is a little bit out of focus. For that, I apologize. But we can see now that our LEDs are blinking away merrily. So that is fantastic. And RapidGPT has proved to me that it can at least create a nice up counter, which is a very, very good place for us to start. So let's head back to the presentation. So that's how we get started. We make a thing. So what are some reflections in general? Now, these reflections here actually are based on ChatGPT, and that's because I've just got a bit more experience with having played with ChatGPT, and as I said, my own entry was based on ChatGPT back when I did this. So my thoughts were that in general, we usually get, something that we can work with. And you would have seen that even with RapidGPT, right? Like that first block of code that it output when I first started, it did have a couple of things, or it actually just only had really one thing wrong with it, which was that it didn't initialize the variable using an initial block. But, you can make an argument that if you're writing code for an ASIC, you don't need those initial blocks, because ASICs actually need proper reset circuitry. Whereas in FPGA-based design, we can make assumptions that all of our registers power up to 0 and things like that. And that's not necessarily true for ASICs. So, you can make an argument that the design that it output was actually pretty good. But yeah, my thoughts are that a lot of these AIs do actually start from a pretty good spot. So how complex a design can we go? And I'm going to try making another design in a couple of minutes, which is a bit more specific. But I want to just briefly mention the design that I created back for the first Efabless challenge. And this will actually answer a couple of your questions in the Zoom chat already. I see there's a couple of QA questions in here. And the very first one is, are there any reference designs? And the answer to that is yes, there's my design, but there's actually tons and tons of Caravel reference designs too. So back when I did this challenge, I started from this prompt here where I wanted to make a little basic 8-bit processor. And you can actually go through I'm going to exit this now. You can actually go to my my repository. If you just Google, I think, Qt Core C1, it'll take you to my QEH Qt Core C1. And from here, you can see the entire Caravelle project, which actually embeds my processor into it. But not only that, you can actually go into some of these folders, and you can actually have a look. I exported all of the chats that I used to create the project. So, and they're ordered. So you can go back to, say, conversation number 1, and we can have a, oops, not that one. Whichever the file is, my apologies. Oh, conversation 0 indexed, of course. So we can, here's my very, very first ever prompt, and then ChatGPT starts to output some answers. And then what we do is we just keep going through the conversation over and over. It goes longer and further. And I was trying to get ChatGPT to make some of the specification for me. So it was really defining its own instruction set architecture and whatnot. Right. And so then we got all the way through to, let's say here, this is conversation 3. And at this point, I was starting to get ChatGPT to start producing code. Now, of course, ChatGPT back then and still now is not properly integrated into the EDA process like RapidGPT is. So the nice thing about RapidGPT is that it can actually, using that merged function, it can actually try to kind of put the code into your files for you, which is really neat. Whereas with ChatGPT, I was actually, selecting everything and copying and pasting it into my Visual Studio Code, which was a little bit painful. So, I encourage you, if you're wondering about, what a good place to start is, to come and check out how we did this for the first challenge. But also have a look at the other entries, right? I showed that slide where we've got all these other teams that have entered. We've had people that created a convolutional neural network accelerator, one for spiking neural networks too. I really, really encourage you, if you're not quite sure how to get started, you've got 9 really, really good examples on how to use AI for the Efabless challenge. So hopefully that'll give you some ideas about where to start looking for some resources. So when I was producing it, that's not what I wanted to push. Oh, no. When I was producing this design, it wasn't a purely linear process. And that's something that I want to stress, is that you will almost certainly have to go back and change things that that you made earlier. It's a very long conversation to get it to produce any kind of meaningful design, right? You just saw me make something with RapidGPT, but it was really not a particularly complex piece of hardware. I was just getting it to count an LED. Whereas if we want to do something like a whole microprocessor, the conversation log gets very, very long and unwieldy. And when you finally put everything together, you might realize that part of it's not working very well, or there are bugs, or there are mistakes that need to be repaired. And that was exactly the case with me. So I got through 9 conversations and then realized, once I built my assembler and I could actually simulate my design, that the processor was not working correctly, right? It worked to a point, but it wasn't working enough for the whole design to function correctly. So what I had to do was go back to my earlier conversations and then continue them. And then from that, try and rectify the situation as best I could by continuing these earlier conversations. So going back to the original specification conversation and saying, hey, this didn't work super well. We need to do a thing, something to do with branches was not quite right. We had problems with the specification. And so because we had to change the specification, we then had to go change the control unit, the data path, and then we had to fix some other bugs and so on and so forth, right? So it's definitely not completely linear. We did end up building this nice little processor though, so that made me very happy. And in fact, this is just the basic version. This is the Qt Core A1. For the challenge, we actually produced the C1, which expanded it to have even more features. And in the conversation log, you'll see there's 2 sets of conversations in here. First, we have the original processor, which was the A1, and then we have the C1, which is where I actually, the conversation log is even longer because I had to go through and try and take advantage of the resources that Caravelle was giving me, and add that extra stuff, which was kind of fun. Okay. So how did we do it? So with this sort of conversation log with ChatGPT, we generated 100% of the Verilog that ended up being taped out to do with the processor itself. We did produce a very small amount by hand, which was the actual interface between the processor and Caravelle. And perhaps that was actually a mistake, because so far in my testing, because I have the actual chip with me now, the only thing that seems to have any bugs is that interface, which I wrote by hand. So take from that what you will. But certainly, there's definitely some interesting thoughts in that the ChatGPT model does have, in this interaction loop, concerns around maybe the scalability of it. We have a finite amount of context the language model can operate over any given time. We have concerns with the fact that maybe it's a third-party model and we don't necessarily want to push our designs to OpenAI or any other third-party provider. We do still have a human in the loop, and as I say, there are bugs which you do have to try and find with test benches. So definitely, I think there's a lot of interest in how we do. How do we actually start automating away some of the sources of annoyance? Like, can we get the language model to fix basic bugs on its own? Do we really need a human to help fix every error? Or can we get ChatGPT or whatever other AI to try and fix those bugs itself, perhaps using the feedback from the tool? So already in this presentation, for instance, you saw that the simulation bug was just, there was just X's being output. And it would surely be fantastic if we could get the tool to realize that, in simulation, it's all X's and then just fix it. I didn't even tell it what to fix, remember? I just said the simulation has X's and it fixed it itself. But because there's not yet a link between the AI and the simulation environment, I still had to do that prompting. So it really would be nice if we could do some kind of fully automated flow. Part of that also would be trying to come up with test benches. We did a little bit of a play, and you can have a look at this paper here on arXiv if you're interested. You'll want to look at the version 1 of the paper, because that has the benchmarks in it, which was looking at, can we get ChatGPT in particular to produce both the designs and the test benches for a limited set of benchmarks? And the answer was sort of, but the test benches really weren't very, very good. So, I think for now, we do really still need to think about how we get human-made test benches to verify some of this AI-generated code. And surely it would be spectacular if we didn't have to do that. Okay, now I promised I would talk about the Efabless challenge, so I've given you a fair amount of background. So what are we doing in challenge 4, right? And this is how I'm a judge for challenge 4, so full disclosure, I'm going to be marking some of your work and grading it. But what I'm really interested in, what I was thinking about is, how would I start about approaching this challenge, right? Like, what would I do first? And for me, the thoughts come down to, well, this is primarily meant to be some kind of audio thing where we're spotting keywords, right? So that implies to me we need some kind of audio input, maybe some kind of audio input processing. Maybe we'll have filters or feature extraction or something like that, right? So that's kind of the thoughts that are percolating in my head. So on this call right now, what I'm going to do is try and make something, right? I'll give myself about 10 or 15 minutes. And disclosure, I have tried this earlier, so I have an idea of what may or may not work. What I want to try and do is just this first bullet point here, right? So I want to just see if I can get audio into my FPGA and then do something with it. And later on, beyond the scope of this webinar, perhaps if I was an entrant, I would then think about what are some ways to start processing this audio input that I'm capturing. Perhaps I could do some filtering or something like that. And maybe if we have time, I'll have a play. Of course, getting it onto an FPGA is just one part of the challenge, because the whole idea of this is that it should be working in Caravelle. So you're going to not only want to validate it in, say, an FPGA environment, but you're going to want to make sure you can simulate it and then put it into the whole process, which is what you will be deploying to within Caravelle. So here's some hardware. This is what you saw in the rather blurry webcam video earlier. I have this Lattice Ice stick, and the thing I like about these ICE 40 FPGAs is they have a fully open source load. flow. And I know that there was another question in the channel. Someone said, oh, I can't see where it's gone, but there was a question that was like, do you have to use an ICE40 FPGA? I don't think so. I think there are some other FPGAs that have open source flows as well, but of course you don't have to use an open source flow for this because this is just for verification. For the webinar, I'm interested in using an open source flow because Yosis is what Caravel uses, and so that's kind of why I have that there. And now I actually have these a whole drawer for reasons of these little microphones that you can get from Adafruit, right? They're like cheap. They're $2 or $3 or something, and they're quite cute. And what they do is they output over an I2S channel a audio stream. So I can actually just plug this microphone directly into my Lattice FPGA, and then I can try and read from it and try and capture the audio. So that's what we'll see if we can do here. Now, if you don't know anything about what I2S looks like, that's okay. I'll give you a quick crash course, and then we'll hope that RapidGPT knows it too. Audio, of course, is a continuous wave. We discretize continuous waves to turn them into digital logic. Or into the time domain, and we sample them, right? So I might have an audio wave that looks like this sine wave over here, and what I can do is I can just take recordings at a fixed interval of the magnitude of that particular wave, and that's what the microphone will do for me. And then as long as the continuation here, any signal can be represented digitally as long as you're meeting the Shannon-Nyquist theorem, right? So you have to be sampling it more than twice the speed of the highest frequency component. Okay, so I'm not going to dive too much further into audio theory. Okay, so we've got this this I2S standard, right, which is what we need to be reading from here. I2S is a serial bus interface. That means that it sends data serially, 1 bit at a time. And it was introduced by Philips way back in the day. And there are sort of 3 signal lines. There's a bit clock, which has a variety of different names. On our board here, it's called a B clock. We have a word select clock, which is choosing whether or not you're the left channel or the right channel. And that's in this board, it's called LR clock. And then we have our data line, which is the actual bits of audio that are being captured. And in that case, it's called DOUT. And on this board, we also have a cell, which determines whether or not the microphone is the left channel or the right channel. And then we've got power and ground, right? So nothing too outrageous there. And this is what the timing diagram for I2S looks like, right? So we have a clock. This is our bit clock here. And that's going up and down, up and down, and up and down, up and down. Our left-right clock or word select clock, what that does is it chooses, are we reading the left channel or the right channel? And then our data line is going to give us 32 bits of data, which is on each of the left channel and then the right channel. And that 32 bits of data is your reading, fundamentally, right? It's the absolute magnitude at that moment in time, the value in this graph of this number. In our case, this microphone actually only uses 18 bits of those 32 bits. So first it promises to only have 24 bits of data, and then it says the other 8 bits are just tri-state. So that's a bit annoying. And then it says that actually of those 24 bits, we're only going to use 18 bits. So it's a 32-bit protocol, but we're really only using 18 bits of the protocol. So that's nice. And then it says here we need to synchronize the word select on the falling edge of the bit clock, which is a bit irritating. And also the first bit is delayed by 1 bit clock. So there's a few different pieces here that we need to juggle to see if that'll work. The other thing we need to know, sorry about this typo that I've just noticed, the design operates as an I2S slave or target, depending on your nomenclature, right? So the main chip, the master, needs to provide both a bit clock and a word select. And your frequency of your word select is going to be your bit clock divided by 64 because there's 32 bits per read, right? Okay, so that's all their thing. That's all it is, right? Now let's see if we can make it in the next 10 minutes. All right. Okay, so I I need to add a few more things to this before we start. And I did that already just for time reasons. So I've just got a little bit of stuff in here, and I'm going to, this is my test bench actually. Or is this my backup file? I've forgotten which one this is. Oh, this is my test bench. Okay. So the reason I wanted this is it's got this beginning stuff, and that's important because it describes my pinouts, which haven't got anything to do with RapidGPT. So I'm going to create a new file. And what we're going to do is I'm going to say, I need to save it first, I suppose. Let's save it as I2S Busmaster. Okay, so this is the, that's my top level. What am I talking about? This is my top level file. I make that because it's just about wiring. But what we do need are these wires here. So we need to have a cell line, a left-right clock, a bit clock, and a dot. And actually, we only need 3 of those. So I2S Busmaster, it's going to have that. We're outputting this one. We're outputting this one, right? This is, and again, this is not something that RapidGPT needs to care about, right? It's really just for me to tell it. I'm defining my specification. So it's going to be outputting the left-right clock and the bit clock, and it's going to be inputting the data from the microphone. I need it to output the audio that it's recording, right? So I'm going to get it to output a 32-bit left channel and a 32-bit right channel. And then I guess I'll get it to output a signal when it's done, right? And I'll call this a pulse, right? So my expectation here is that, why is that purple? What have I done wrong here? My expectation here is that the, I don't know why that's purple. That's strange. My expectation here is that the design is going to operate continuously. So I'm going to just put that in as a comment here. So make me an I2S Busmaster with the following IO. Okay, and this is my instruction to RapidGPT. And I'm going to just give it some instructions here. It should operate continuously and capture the left and right channels of I2S, deriving all timing from CLK, which is at 12 megahertz, because that is the frequency. I guess we need to give it a frequency to work from. So I have this other one here, which had a bit more specification. I'm just going to copy it over because otherwise I'll be here all day while I'm typing it in. Okay, so what I told it here was this set of instructions. So I'm just going to copy that over from my other window, but don't worry, it's actually pretty straightforward, right? So this implements a busmaster for the I2S protocol. It continuously captures 32-bit left and right channels, outputs to channel L and channel R, and then sets this, I called it capture done, but it's a pulse. Capture done pulse signal to 1 after each capture. The I2S bus is assumed to be running at 1.5 megahertz. So you can see I'm giving it a lot of like detailed stuff here. Okay, so this is sort of my prompt engineering, right? So what I'm going to do now is I'm going to close off this comment block and we'll see what RapidGPT does. Full disclosure, I did have to do this a number of times myself before I got it to work, hence why this comment block is very exacting. So maybe it'll just remember what I told it last time, and it'll work first try, which would be quite nice. This is definitely a harder design, right? Because now there's so much more going on than just a single piece of an LED going up. And so as a result, it's thinking comparatively longer. And I'll just give it a couple of moments more. And what I'll probably do, because I'm just having a look at the time here, is I'll do a quick simulation. If it works, fantastic. But if it doesn't, what I'll do is I'll just head over to my other Visual Studio Code window, which has my answers from when I was trying this about 2 hours ago, because that one, I know it'll work. Oh, here we go. We've got something. Let's have a quick look. So we've got some dividers. It looks like it's going a shift register to capture the data. Honestly, it doesn't look completely terrible. So let's give it a go, shall we? So what I'm going to do is I have to join it to this design here. So I have to just change which one of these is my top level. So I'm just going to... And my new top level is this one. This is a bit painful, probably. So now I have it actually instantiating my nice bus master here with the appropriate signals. Although I foolishly renamed that signal. I don't know why I did that. So capture done pulse here. And I just need to modify my make file so that it also includes my new file that I just made, right? Which is this i2s busmaster.v. Okay, so let's... Oops. So that didn't compile. Why didn't it compile? Probably because I accidentally used the wrong name. So I called it channel L and channel R, which is backwards. Good. I like setting traps for myself when I code live. Where's my text top and bottom? So this is... And I also apparently renamed my other things. Why did I do that? Why did I do that to myself? Okay, so here I've called it I2S LRCL, and in this one, it's called clock and out and 12 megahertz. Okay, so I did a lot of the things to myself. That was... Okay, here we go. Simulation worked. All right, let's have a quick look and see what it looks like. Lots of red. So once again, we're not fully instantiating. It looks like we're not giving ourselves initial signals for some of these. I'll just quickly edit that by hand because it might work if I do. So if I head back to the bus master, I'm just going to, where it's made regs, I'm just going to just drop in this nasty hack to just set everything to be 0 to begin with. And what that will do, of course, is give it those initial values that it needs to... Oh, some of them it did it. Okay. And what that should do is give us the initial conditions. Okay, no, it's still not 100% happy here. It looks like the data out signal isn't being set properly. That's my test bench. That's at fault. Okay, that's my fault. Okay, so what I'll do, just because we're running low on time, is I'm just going to switch to my other window. Ta-da! And this is the answer that it gave me. So we can have a quick look in the make simulate view. And we can have a quick look here. And we can see in the simulation now that we get our bit clock coming out. After 32 of the bit clocks, we get a switch in the left-right clock. And that's nice. And we can actually see here, as we increment each bit clock, it's actually slowly shifting in. This is probably the best place to look at it. You can see here it's slowly shifting in that data. And in this test bench, my data in is just set to be, 1. So that's nice. And I did have to do a couple of attempts. I can go back to the conversation log, and you can see here I did have to go through a few things. But honestly, it did a reasonable job the first time. Not the first time. It did the reasonable job once I gave it this comment, right? So the most important thing here is actually the quality of this comment. And maybe you would look at this and go, I don't think that's a very good comment. But the quality of the comment here is what I mean is this gives it enough information that it was actually able to produce this, and you can see that it did actually produce it. In a single pass. And to me, that's really important because I have found in my experience that the higher the quality the first response is, the more likely it is to actually work for you. And we've got just 2 seconds left before I head over to questions and answers. So what I'm going to do is I'm going to just actually plug in my microphone here. I'm going to now synthesize the design that RapidGPT made. And yeah, that's working. So you can sort of see there's some blinking lights here. What I'm doing is I'm outputting the highest magnitude bits from the audio just directly to the LEDs. So when you see them light up, that's in sync with my voice. If I'm quiet, the LEDs go blank. And when I talk, it's louder, and so the LEDs light up bright. Okay, so we're actually recording this live based on hardware that was made by RapidGPT. So that's quite nice. Okay, I'll also note for your interest that I managed to produce a working design using ChatGPT. And of course, I also managed to produce a working design using GitHub Copilot. So all 3 of these actually did produce quite different answers. But all 3 of them did eventually work. Although I will note, if you when I go to ChatGPT, you'll see how many different times I had to try this prompt with ChatGPT, looking the thing on the left there, just to get that audio to come out. And it was exactly the same with RapidGPT. I think it was about 10 attempts at least for each of those AIs, just slowly changing that prompt each time. And in terms of tips for the prompt, again, it's all about giving it as much information as a human would need, at minimum, to actually produce this design, right? So this really does have everything that it needs, that a human would need. I could hopefully give this to a competent engineer, that block of comments, and have it actually have the human produce this design as well. I had no success when I just said, make me an I2S busmaster. I really had to describe it in detail what I actually wanted. Okay, to conclude, you probably have to try multiple attempts. You do need to use prompt engineering, and I didn't show it today because I ran out of time, but they also aren't super good at coming up with test benches, which is why in the demo I did have the test benches that I had produced. So I do want to say good luck with the challenge, and thanks to Efabless for sponsoring this, and thanks to Primus for sponsoring part of it as well. I think it's a really, really exciting time to try out this sort of stuff. I'm very passionate about it, and hopefully you can try out some things as well. So thank you very, very much. And what we'll do is we'll go over to questions. Mohammed, did you want to?
Yeah. So thank you very much, Hammond. So I'm going to I answer some of the questions that are just relevant to the information around the challenge. Some of them I will help answer, but also just let's start here. So Harsh Sharma, I read your MLCAT paper on ChipChat on scale 0 to 100. How can we do that? The testability, and how you took care of in your chip. So I'm thinking, how did you take care of testability or verification?
Yeah, so as I say, that I've always struggled with getting all of the models to write good test benches. That ChipChat originally, all of the testing was made with test benches that I had produced. So we focused on that work exclusively, getting ChatGPT to write the functionality code, the code that was actually being synthesized. Code that wasn't being synthesized, I wrote in terms of the test benches, and then later on the actual Caravelle test benches as well. But those were based on, of course, the examples that Efabless provided.
Yeah, the next question is, I'm very interested in generating code utilizing a set of specific APIs, like example, generating Python code that's using Verilog to generate a Verilog code. Could you share any ideas on the effective ways to do that?
Yeah, effective ways, exactly what I showed here, right? So just as you're saying a specific API, you saw me when I prompted, when I was prompting RapidGPT, I always gave it my API, right? I always gave it my module definition so that I knew the I/O it was going to produce. And I also described, in many ways, what the behavior of the API is, right? So as long as you describe the behavior of the API and then you describe the connectivity of the API, that's a really good place to start from. And then from there, just work out what information you want to go from there.
Okay. I hope that answers the question. So the next one, have you tried Claude Opus somewhere?
In my research group, we have tried Claude a couple of times. I haven't got any formal results to share. In general, we've always found that the OpenAI models have outperformed almost everything we've compared them to. But I will admit we have not done a formal comparison of the OpenAI models versus the Claude models.
Great, great. I'm an analog IC design trainee engineer. I was asking how someone can use ChatGPT for analog IC design. So if you don't, I'll take a stab on this. So there is work actually going around around the analog design. You can actually use ChatGPT with the right exchange or prompt to generate circuits for you. It would not necessarily be targeted to a given process. Maybe you can use the open source process because it's actually the PDK is publicly available. So I have personally done a few of these things just at the schematic level, the netlist level. Okay, so you can start there, but it wouldn't be able to say, hey, I want to design an ADC. Again, similar to what Hammond is saying, you need to partition and actually go be more specific. Okay, just curious, how did the FPGA synthesize the initial block?
It doesn't. It ignores it. Right. So FPGAs, the initial blocks are not synthesizable, but they are needed for simulation.
Okay. DRC, ERC lib in Rapid GPT. I would leave that question for premise.ai, but there is, conceptually, I would imagine that these things are, you'll see them being embedded into every part, every design step in the VLSI. So, but I'm not sure what Rapid GPT's roadmap is. Okay, is there any LLM that can help analog design, something to help different SPICE syntaxes? So again, I'll say the first one, similar to the first one, you can actually have certain blocks designed using a schematic level, using, for example, ChatGPT. Now, my understanding of the question is that different SPICE syntaxes is like you're trying to translate from one simulator to another. I haven't tried it. I always use open source simulators, and I don't have any data about that, but you can try.
Yeah, so the next question, I'll just quickly jump into it. It's why do we sometimes have restarts and sometimes not? So the number of restarts here refers to how many different times did we give the exact same prompt to the language model to get a different answer. And that's because all of these language models, Rapid GPT, ChatGPT, Gemini, Claude, they're all non-deterministic. And if you give it the exact same input, you'll sometimes get different outputs. Which means, if I'm confident that my prompt is good, I can just try the exact same prompt and get another answer. As in terms of why does it decrease over time, as I got better at prompting the language model, I didn't need to use that so much. So you can kind of see that not only was I getting better at, in some ways, maybe ChatGPT was training me because it was showing me that, I was beginning to intuit what are the better prompts for this particular process.
Yeah, this is I think it's a philosophy question. Which do you feel comfortable chat with, the chip chat or a human IC designer?
I like chatting with both.
Both is, yeah.
Yeah. I don't think you get as good of a conversation out of a language model.
Please share the link to the benchmark results.
If you want to look at the benchmarks that we've done, you can just look at, here it is. So you can just Google this. It's called Chip Chat Challenges and Opportunities in Conversational Hardware Design. For various reasons, it's actually the version 1 of this paper. If you have a look at the PDF of it, which has got that table of results in it, which I briefly showed. So you can have a look here at how this worked and some of the different feedback. The version 2 of the paper just has the results of the Carabao competition that we participated in.
So the next question, and then we're past time, but we still have a few more questions. Once you get the LLM working with efficiency, how do I convert into Verilog like real function? I don't. Is that a
Yeah, I think that's going to be a journey that you discover along the way. Good prompting and time.
Yeah. Okay. The next question is a little bit long. It has twofold sides. Most of these LLMs are getting coding training from GitHub, where HDLs are probably less than 5% of the total corpus. And then how do you think LLMs would eventually get there and become actual experts in HDL designers?
Yeah, so both of these questions are great, and actually I've spoke about it not on this webinar but on other ones that I've done in the past. Right, there's a desperate shortage of open source hardware which language models can train over, but not only language models, also humans. So I'm a big proponent of more open source hardware being done in this space, and it's one of the reasons why I get so excited about working with Efabless, because almost everything, if not everything, Efabless has ever taped out is open source. So, you know, we're slowly over time getting the super rich repository of real chips, which hopefully the language models can also learn to train from. And then as it for second question, I think that's more of a business level decision. But certainly large language models can also help you write glue logic to join various IPs together as well.
Yes.
Yeah. For the next question, I'm actually so glad that someone asked this because I can show it. So ChatGPT can input images, and you will see I tried that. So I took a screenshot of that slide that I showed you guys, and I actually I put the screenshot in as my specification, and then I just gave it this Verilog interface as well, and then I described it a little bit too. But actually, I tried this a few times with the different with just a screenshot and just an interface. I think even maybe this one just has the screenshot. Yeah, so this one is just the screenshot and the interface. And I was really amazed because it could actually read the text out of the image. Like, I never called anything WS, and it said here that there's the word select line. And so it is actually interpreting stuff out of the image, which is cool. It's not ignoring it. As it turns out, though, this image is maybe a little bit too complicated for the language model because it didn't perform as well as it did later on when I stopped using the image. It almost did it, I will say. I think on the third time I tried using the image, this design almost worked. The only thing wrong with it is it was missing the very, very first bit, because you're supposed to capture it on the first rising edge after the last falling edge. And it wasn't getting just that bit there correct, but everything else was correct. So you were just missing the most significant bit. And I was really genuinely quite impressed that it was able to do that. So definitely, yeah, there's going to be some interesting things about putting in the images to give the specification too. So I'm so pleased that you asked that question.
Okay, so I'm gonna the next two questions are just I skipped them. Well, there's a recommendation here from an anonymous attendee. Just please use ChatGPT 4 instead of RapidGPT. ChatGPT is much easier to operate and understand. Now, I think you can comment on it, Hammond, because you used both.
Yeah. I mean, so I only started using RapidGPT literally yesterday. I will admit, as I said during the presentation, there's a few things that I find a bit peculiar, like the merging behavior, where the button is called revert for some reason. And it took me a little while to work out how to get the autocomplete, because you have to put the /* comment. You have to do that. I will admit the documentation didn't seem to show that. It was only when I saw a video of someone actually using RapidGPT that I realized you had to do the comment in that particular style. So I do think that, you raise a good point that ChatGPT is easier to operate and understand. And maybe that's something that Primus can work on. But I will admit, once I worked out that I had to push revert to bring my code in, I really, really liked the feature that I could merge the code directly that that Rapid GPT was suggesting, and I didn't have to copy and paste things in. So, you know, there is a feature that I like there. Eric has asked, which language model do I recommend? All of them. You know, they all have different strengths. I've used ChatGPT the most, as I said. I've got a lot of experience with prompting ChatGPT. I completed the thing that I showed you today using 3 different language models: Copilot, ChatGPT, and RapidGPT. Copilot is really nice because in many ways it does the least, so it relies on you to put a lot of the work in, as it will, and it just kind of tries to speed you up. But of course, it's a little bit less fun because then it's not 100% written by AI. So for the purposes of the challenge, we prefer the models that really write all things. For RapidGPT, would you be able to describe what's going on and fix it through feedback loops? I tried many times and it sort of worked. So you did see me do it with the LED one, for instance. So, you know, I said, I need you to put an initial block, and then it did. And then I said, I want you to change it to 24 bits, and it did. So sometimes, yes, that's true. As I say, RapidGPT and ChatGPT both gave me answers that fully worked. So I can't say that one was better than the other. A question for you, Mohammed.
Yeah, so there will be another webinar demonstrating Caravelle and OpenLane. So to be able, so this one is talking about the front end of the design problem, and then we're going to have another webinar to talk about how do you take the RTL all the way to tape out ready silicon or files.
Okay, would it be better to use large language models for CocoaTB or Verilator? Can't comment. I've used Verilator in the past with language models for some success. I personally have never actually tried using a language model for CocoaTB, but I do believe some entrants haven't they, Mohammed? I feel like in...
Well, I think because of CocoaTB and both the CocoaTB as a framework and Verilator are open source.
Yeah.
I would try it. I would, you know,
try it. Yeah.
Yeah.
I'm fairly confident from memory that someone in the second Efabless contest used CocoaTB that with tests that were written by language models. So people have definitely done it.
Yeah.
Is it possible to generate system Verilog assertions? Yes. And in fact, I have an archive paper on that as well. So if you want to look up some of my academic work, you can just look up, I've forgotten the name of it. Security assertions by large language models archive. And here it is here. So we actually do have a paper which has just been accepted by TIFFs, which is a venue, don't worry about it, which is literally trying to explore this very question. So if you're interested in the answer to that question, do just have a search of that title. You'll find your way to this archive paper and you can have a look. The general answer was sort of. They sort of wrote assertions. Sometimes they wrote good ones, more often they wrote poor ones.
Okay.
I think we've already answered that next question again. So Pete asked about UVM test benches again. Try it.
I think Eric Berg, or one of the guests that we had on our webinars, he's been using ChatGPT specifically for generating the verification test benches and in a framework like UVM. So I would try it as well.
Yeah, definitely. Someone has suggested using Rust. Again, this is all the same sort of like use a higher level language and compile it down. Definitely, you know, high level synthesis. I don't know about Rust, but certainly people have seen success with trying to write hardware in Python and in C and in Chisel and whatnot, and compiling it down as well. Thanks for the comment, Jadok.
Yeah, so this is a follow-up question on the previous question. Actually, I was a little bit I'm glad there is a clarification here. My original question was actually about generating Python code utilizing specific functions in a specific Python library. I guess Anza should be providing enough explanations on the functions as Dr. Pearce suggested.
Yeah, and that pretty much is, right? So the more, if it's a very popular Python library, you often don't need to because it's just seen enough examples. If it's not a popular Python library and you can't give it the source code or something for it to learn from, then yeah, just give it more context and you might be pleasantly surprised.
Yeah, so we have a volunteer here. CodeDB works with ChatGPT, but sometimes it hallucinates functions that don't exist. So thank you for that input.
Yeah, thank you very much to the audience. Thank you,
Thank
Mohammed,
you.
for hosting us.
Thank you. Thank you, everyone. And then the recording will be coming out with a link to everybody that registered. Thank you for making the time, everyone. Thanks, Hammond. And have a good day and evening, wherever you are.
Thank you.